Yeah, so in last lecture we were talking about doing measurements in different bases. So we're combining this idea of performing quantum measurements, but also the fact that you could measure things actually not just in this, say, 0, 1 basis, but also in any other type of orthogonal set of bases. So this sort of follows on a little bit from that idea, but kind of takes it in a slightly different direction. So what this one, or this set, is going to be talking about are actually sort of observables. So what we've been talking about is just kind of probabilities. So whenever we make some measurement, basically all we were saying was that we get some probabilities in the end. But how do you relate that to actual kind of observable? So what kind of my cartoon here and the opening slide is supposed to show is, so we've got our measurement device. The particle, goes inside the measurement device. We get some readings, and that's going to eventually give probabilities, and then we have this knob to say what kind of measurement we're going to be doing. But how do we convert all that information into something that is kind of more physical about the particle? Because at the end of the day, this guy here kind of wants to know something about the particle, right? So he wants to, know, okay, so, what property of something about the particle this has. And that process of going from kind of probabilities, whatever we were talking about last lecture, to observables is basically what we're going to talk about today. Okay, so so we started off by saying that sort of the quantum wave function is something that has basically all the information there is to know about a particular kind of object, right? So that's like everything there is to know about the object. So what that should mean is that any kind of physical property like position or velocity, angular momentum, energy, all these things that kind of associate with particles, it should all be there in that wave function. Okay. Now you might be thinking, well, we've been talking about sort of qubits, like 0 and 1. Surely that can't contain very much information, and you'd be right. A qubit state, basically that's actually only looking at really one part of the wave function, and often what you do is you kind of simplify whatever you're talking about so that you just sort of focus in on some aspect of the particle. So maybe those 0 and 1 states could be something, just one aspect of the particle. For example, this particle here, it might go left and right. And so we were saying, like, if it goes left, it's 0. If it goes right, it's 1. And that's fine. Of course, there's all kinds of other properties of the particle. So, is the particle, in what is the velocity, or what's the position, say, in this direction? We're just talking about left and right. What about up and down? There's all kinds of other properties that the particle might have, which we could also put in the wave function. Just makes it more complicated wave function. So what we've basically been talking about is just like kind of one aspect of the wave function. Okay. So of course, if you want to find some observable, so say this guy here is going, okay, I want to know what the energy of the particle is. Okay. So, you know, that should be some kind of number, right? So energy, okay, energy particle has 3 joules or something like this. So we have to convert that measurement that we did into this kind of observable. And so there's always a measurement kind of involved when we are talking about an observable. So let's jump into a kind of an example. So you know, it's nice to just start with a kind of an easy to understand example so that you sort of get the feel for it. So let's sort of make up this kind of particular kind of scenario. So say you have a bunch of boxes and they're all lined up and they're all evenly spaced. So maybe they're like, you know, 1 meter or 1 centimeter, or it doesn't matter, some distance apart, and they're evenly spaced like that. You know? Okay, and then say this particle could be, well, firstly, there's only one particle, okay? So there's just one particle, and say that one particle could be in any one of those boxes, all right? And so, classically speaking, of course, it would be either in box 0 or box 1 or box 2 or so forth, right? But from what we've been talking about so far, well, quantum mechanically, it doesn't have to be only in 1 or only in 2 or only in 3. It could be in some kind of combination of those, and then we would write that as some wave function like this. So the 0 means it's in box 0, 1 is in box 1, and we're allowed to have some kind of complex coefficient on all those states because, well, we live in a quantum mechanical world, so why not? Okay. Now, okay, if we did this in this room, this would be really hard to do actually because, well, won't go into it so much, but basically such quantum states are really fragile and then they kind of break easily. But you can do it with kind of smaller systems, and so here is something that's a lot like actually this example. So how you might actually do it in reality would be something like you can tightly focus laser beams, and if you put this whole thing in a vacuum chamber and you have a particular kind of frequency of light, what you can arrange is that the atoms are kind of attracted to this very highly intense light. So the atoms tend to kind of want to sit over here. And then if you have this one atom, then you could put it in this kind of quantum state where it's sort of partially in this region. And so obviously this would be kind of corresponding to these boxes. And the atoms could sort of, you know, kind of be in both box 7 or 6 kind of together, right? So if you're interested, you can look up that paper. That's how you would actually do it, this kind of experiment. Not actually with boxes, but conceptually, you know, in a perfect world, you could do that. Okay. Now, so we prepare it in this quantum state, so it's sort of some kind of superposition of being in all these different boxes. And then we get our measurement device, get our measurement thing, and basically the measurement device goes, okay, so I want to know, is it in box 0, 1, or 1, or 2, or 3, or 4, 5, 6, or 7? So it kind of says, okay, let's figure out exactly where this particle is. And so as we've learned, what that does is that it changes the quantum state. So even if it started like that, that act of measuring it kind of destroys that state. The wave function collapses. It ends up, say, in this time that we did the experiment, ends up in this one, and then so you go, it was in box 5. Of course, it wasn't really. The measurement that you did kind of destroyed the quantum state, the random collapse, and the probability of it being there. So if you run this experiment many times, then sometimes you'll get it in 5 or 4 or all these other ones, and that just depends upon the this coefficient here. So if you square that, modulus square that, that tells you the probabilities that these come out. Yeah. So that's kind of a little bit of an extension of what we were talking about. We were mainly talking about qubits here. Now I've got states from 0 to 7, but it's basically the same idea. Okay. So now, so we've got our data. So we've done our sort of experiment. So now we say, or now we ask, or this guy asks. So now I want to know where was the particle. Okay. So where was it? Was it in 0, which box? 0 to 7. So of course, it's quantum mechanics. It's like it's a wave, right? So like we started in maybe first lecture, this question doesn't actually even make sense because it's in sort of all the boxes and it's in this quantum state. But to some extent, we do know how to sort of answer that because essentially after you've done your measurement, this is just like it looks just like regular probability, right? So even though it's kind of random, we can do stuff like that we used to from probability theory and start talking about, okay, well, we all know it's random, but we can say, okay, but I can tell you that on average, because I've lined the boxes all in a line, on average, it's at this position, 4.3, because you can take an average of this, they're all in a line so that, on average, it's actually about here. So I can do that. So, so quantum mechanically, if you wanted to sort of, ask, say, what is the energy or what is the position or momentum or all these types of things. All these things are usually kind of random, right? So it's not in any particular energy or position. Of course, it can be. It can be. You can have a wave function where it's just only in 5, so that's allowed. But generally speaking, it's usually some kind of random thing. And so rather than saying, oh, it's just random, you say, well, we all know it's quantum mechanics is random, so you can say, yeah, on average, it's here. Right? So the average position is this. And likewise, you could do something like this also for energy or momentum or anything like this. You could measure the energy of the quantum particle. Sometimes it's a bit high, sometimes it's a bit low, but you can talk about averages. So so we can talk about averages, and we can also talk about variances, standard deviation, stuff like that. So another kind of quantity that you could equally talk about is the variance of the position in this case. So that, of course, tells you sort of how much it's sort of, or how wide this distribution here is. Right? So variance is, of course, a measure of sort of how sort of wide it is. In the case of this, it would be probably the whole width, right? So the standard deviation, which is sort of a measure of the width, we probably, eyeballing it here, the average is 4.3, is probably plus or minus 3, something like that. Okay, so actually the basic idea. And in a way, so this is how you talk about observables always in quantum mechanics. So it's in the sense of, averages, and, sometimes you talk about standard deviations. Of course, you can talk about higher moments if you really want to. Now, what I'm going to talk about from here is just a kind of the mathematical formalism to calculate these things, and there's a sort of a very nice way of doing this, which kind of has a nice okay, so it'll eventually explain why we're using this kind of notation in the first place. Okay, so suppose let's make this a bit more general. So suppose we have some general observable Q. So this could be things like position, momentum, energy, something like this. And what we always have with this such an observable is that there are particular kind of states that we associate with particular values. So we have a bunch of kind of definite states here, let's call that n, and these all have some definite numbers associated with them. So, example of that would be these boxes, right? So each one of these are the different states, so this is what I would call n, and each of those different states has a number associated with it. That's the position. So this is where the position 7, 6, and 5. Okay, so these Q's are the numbers, and the N's are, this is the states of being in each box. So then, now if we have this state, so we've got this arbitrary quantum state with some coefficients A, then of course we know that the probabilities that we're going to get for each A is just the square of it, rule that we've been dealing with so far. And say we want to take now I want to take the average value of it, whatever this Q thing is, right? So then of course, so I'm going to use this notation for average value of Q. This kind of, just apart from the quantum mechanics, did you guys use this type of notation when if you're talking about averages, you put in this kind of bracket? No? Okay. That kind of notation sort of often somehow, well, it's quite common in physics at least. So the average value of Q, we say, is of course the probability multiplied by whatever the value is. So that's, say, position or whatever you're dealing with. And so it's just probability times the value, or we can write it explicitly in terms of this the wave function modulus square. Yeah. So this was kind of relatively easy because, hold on, let me just let me change the order of what I'm talking about here. So a neat way to work this average out is actually using the so-called observable operators. Okay. So let's kind of do exactly what you just did there, using these observable operators. So what we had before was that the average value of Q was alpha n squared times q. So that's what I had on the slide before, right? So a wave function here is an. So that's our probabilities, yeah, and that's the values of this q, whatever it is. Q could be position or energy or whatever, right? So this is our observable. Okay. So this is observable. Okay. So what we're going to define here is so-called observable kind of operator. So this is kind of definition. Okay. So what we do is this is obviously a matrix because it's like we've got this outer product structure, right? And essentially what we do is we put on the diagonal elements with respect to the states that we're talking about, the value of the observable that we're talking about. So e.g., so n, this could be like the position, and then the qn would be the 0, 1, 2, 3, like before. So if we define this thing, there's, we obtain this just kind of, it's like kind of through our just regular knowledge of probability. But there's another way of sort of getting it in a way, and this is to do the following. So suppose we calculate this quantity where we have this is a matrix, this is our state vector, and this is our conjugate vector. Okay? And well, I'm just going to go and just calculate what this thing here is. So conjugate vector of this one, an star n. Okay, so that's this first one. Q, this is the definition. Now, I have to be careful because this sum is a different sum to this one. So I should put a different index on this one. So this is our Q. And finally our state psi. Again, I need a different index. Whoops. A-N. Okay, so this is the thing that we need to calculate. Q's and A's look a little bit too similar. Okay, so that's Q, that's an A. Okay, so I think, a couple of homeworks ago, I made you calculate something like this, and didn't say it was an observable, but this is what it was leading to. So let's first do the product of these two. So here, so let's put both of these sums together. Qn, this is an prime prime, n prime, n prime, n prime prime. Okay. Now, you see how you might simplify this one? I'll give you a bit of a hint. So this part, what should this part be?
if they are the same, they should be 1.
Right, yes, exactly, yes. So this thing here should be equal to 1 if n prime is n prime prime, and it should be 0 otherwise. N prime not equal to n prime prime. Yeah. And we like to call this so-called Kronecker delta. Okay. And you've probably maybe seen this more in context of integrals and stuff, right? You've done the delta function in integrals and stuff like that. Yeah. So it's exactly the same kind of thing. So if you've got delta function f of x, this is just equal to the value there, right? So basically like that, this integral kind of collapses to just a single value here, where the, well, this is equal to 0. Okay, so it's a lot like that, but it's just the discrete version with a sum. And basically what happens is, it's actually quite simple, is that basically this n prime has to be equal to n prime prime. So basically this double sum here turns into a single sum, because it's going to be 0 unless the n prime is equal to, n prime prime is equal to n prime. So then just replace all the n prime primes with n's and just remove one of the summations here. Then it's equal to that. Okay, and let's keep going here. So now I've got two sums n prime, and we've got a n star, q n prime, a n prime, and we've got n overlap with n prime, n inner product with n prime. Then can we see how this one simplifies?
It's the same.
Yeah,
It's
same.
the last step.
Yeah, same as the last step. So this thing is delta n prime. So again, the n prime turns into n, and then one of the sums disappear. So it's a n star, q n, a n. And this is a n star, a n. So it's a n squared, modulus squared, q n. And actually that's exactly like that thing there. Maybe let's do it also another way, just so that it's more obvious. So let's do it the matrix method. Matrix way. So in this case, the state is A0, A1, something like this. This Q matrix is the matrix that looks like this. Qn, everything here is 0. And of course the conjugate vector is just this one, but laid on its side. So in other words, what we're doing here just A0 star, A1 star, dot AN star. Got this matrix Q1, Q0, Q1, A0, A1, and so you can see, because this whole thing, the diagonals are 0 here, right? So when you do the matrix multiplication, you're going to end up with like A0, Q0, A1, Q1, dot, dot, dot. You can actually see this thing, so what we did here in more this kind of vector kind of way, this thing here, we've got this Qn dash An dash thing here, that's exactly that vector there. See, this vector here is actually that vector. And then the second multiplication that we're doing here is actually just the multiplication of this one with this row vector. So when you do that, you can see that you're going to get some stuff like A0 star, Q0 plus A1, A1 star. I shouldn't have used Q. Okay, so A0 star, Q0, A1 star, Q1, dot, 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 dot. And that is exactly that, and that's equal to that. You know. So what that basically says is that actually this thing that we just worked out, which was, remember we just did this from probability theory, right? Probabilities times by some value, averages. So there's a kind of a neat formula for working that out, and that is simply to do this thing, right? So it's like you have your state, you have your conjugate step version of the state, you sandwich it between this operator, we define it like that, and that's our expression. And that gives us our average value. Now if you're thinking, okay, fine, that's average values, but what about variances or anything else? For that, well, it's still pretty easy. You just of course, variance, say we want the observable that's the variance of Q, so this would be like, the width of the, say, position. If Q is position, it would be like the width of your position. Then, of course, this thing is equal to average of Q squared minus Q average squared. And these things are still defined in terms of those averages, right? The variance is just the difference of two types of kind of averages. Well, this one you square, but and so basically what this one means, actually, we can just reuse this same formula. So whenever we want to work out the say the average of this Q squared observable, then it's just Q squared where you square this matrix. And then after you square the matrix, then you just sandwich it between two of the state wave functions. And for this one, it's just, okay, you calculate the regular average of Q according to the same formula that we did here, then we square it. that make sense? Yeah. Okay. Okay, so so now let's go back to whatever I had over here. Okay, so actually, so you know, this looks like pages of algebra. Actually, that was the easy case. This was actually kind of easy because for the observable Q in the state psi, it was actually written in the same basis. Okay, what do I mean by that? Well, I mean that when I defined my Q here, remember I started off, you know, these were boxes, right? You know, here's box 0, box 1, and so forth. And the value of these things, Qn, this was 0, 1, and so forth, right? And then my state was also written in terms of zeros and ones, right? So it's called A0, A1. So these states here that I wrote my basis in, and then these zeros and ones here, for whatever I'm defining my observable, they were kind of the same states, right? So that's why we could use this orthogonality property here, because I know that 0 and 1 are different states, and they're kind of orthogonal. But it doesn't actually have to be that way. Maybe I could have had my state written in a kind of a different basis, right? Because remember, you know, in that 2-qubit example, I had my state like here, and here's 0 and 1. But, you know, maybe I could have chosen to write my state in a different basis where my axes were all different, right? So my state could have been written in, for example, for the 2-qubit example, I could have written this in terms of some other bases like, you know, plus minus basis for a qubit. Yeah. Okay, so if I wrote my state in the plus minus basis, but then my operator was defined in terms of this 0-1 basis, then, you know, how do you calculate that? It's basically what we're talking about here. So, in that case, what we'd have to do, well, there's kind of a couple of ways around it. So firstly, of course, the first option would be just to convert our state and rewrite it in the basis of whatever the observables are in. So if we were unfortunate enough to have the state in plus or minus basis, but our observable was 0, 1, then fine, we just rewrite this so that it's in plus minus basis. So for example, here it would be something like b0 plus b1 root 2, 0 plus b, you know, this one. Okay, so now I've rewritten it in the 0, 1 basis, so now I can go and just do the same thing that I did before, just with the right coefficient here. So we could do that, or actually, another way to do it is, and this is kind of why this formula is kind of neat, is that we can simply stick it into that formula, and it still actually will kind of give the right answer. So despite the fact that our state might be written in terms of some other coordinate system, if we just introduce it into this formula, actually it will still give the right value. And this bit of magic happens basically because, well, it's not really magic, it's kind of how it's sort of supposed to work. So if you say we've got our operator, and what I'm going to write here is that these m's, this is like the basis for the r's, for this r observable, and the psi I'm going to write in terms of n's, and the n's are in some other basis, which are not necessarily the same. And if okay, so right, okay. Yes.
So question, so the R is actually Q written in another base?
No, so yeah, but, maybe you could think of it like that, but here I've just on purpose introduced another observable called R, which is, let's say, it's a totally different observable, but it's using a different basis, and these R's are also different numbers. Okay, so what I'm trying to argue here, I think, hopefully I can convey this because you even confused me for a second here. No, I wrote it. So what I'm trying to convey here is that we could either do this two ways of what I said at the beginning. So if these things are in a different basis, one way would be to simply rewrite it in a different basis and then just use our usual, use kind of the same formula as we did here. Okay? So in that case, for example, here, if we rewrite this in here in terms of, where is it? Yeah, here. So we rewrite our wave function in terms of the b's. Okay, so the b's are now written in the correct basis. And then we just use the same formula as we did before, which is to square the probabilities and then sum it over with the coefficients. So that would be one way of calculating the R matrix, the R average value. Or we could simply substitute it into this formula, and basically what it turns out to be is that you get some value that looks like this. And this quantity here turns out to be exactly what the conversion from A to B is. So simply putting it into this formula or doing the conversion and then doing it kind of the same way that we did basically gives the same result. That's basically what I'm trying to say. So, I think it's sort of, maybe I could have written this part a little bit better, I have to admit. Okay, but that's basically the point that I'm trying to get across, that you can either do the conversion and then use the same way, or just substitute everything into this formula, and then you will get the same answer. Okay. deciding whether I should go through this or not. Maybe we should go through like a simpler example. How about that? Because it's all here on the slides if you want to go through it. But maybe what I'll do is to kind of illustrate this point with just a qubit example instead. Okay?
Yeah, sounds good.
Yeah, okay. All right. Okay, let's make some space here. Okay. So let's start with a qubit example. Oops, Okay, so let's say our state is A0 plus A1. I'm going to sort of try and follow the same notation as I have here so that you sort of get the basic idea. Okay, and then suppose I have an observable. So in terms of what I've been writing on the slides here, like my Q observable would be an operator that's in the same basis as here. So maybe it would be like Q0 and Q1, or written in matrix form, it would be just something like this. Okay. That basically means you measure in the 0, 1 basis, and these are the values you assign. Now the R would be some other observable, different one, but it would be in a different basis. Let's say it's in the plus minus basis. Okay. And this observable, so basically what this one means is that it says basically please measure the system in the plus minus basis, and then when you get plus, then give it a value R0. If you get minus, give it a value R1. Okay. That's basically what this one says. So Q and R are different because basically you have to do a different physical measurement. You have to measure in a different basis. So, and if we want to write this in terms of a matrix, we can. So, well, I'll have to do it part by part, but I've done this sort of enough so that I can about sort of so this one written in terms of this
so we were writing R, the matrix R in terms of the basis of Q, right?
yeah. So just to be consistent, because if we're going to write it in like matrix form, we better, so exactly. So if we're writing R in the basis of plus minus,
It would be simple.
it would be exactly like this.
Yeah,
But
so
because I want to write it all in the same 0, 1 basis, like this, then in the 0, 1 basis, this will look like that, and this will look like this, and so basically this is going to look some matrix that looks kind of like this. Okay. So 2 by 2. Okay, and so method 1 would be kind of what I'm talking about here. Where is it? Here, yeah. So when I'm talking about observables in other bases, when I'm talking about here, method 1, basically write psi in the plus minus bases. Okay, so that's basically step 1 of psi, and well, we did this a couple of lectures ago, so maybe I will just skip to the answer. But you might remember that it's going to be like this. Yeah, look familiar? Yep. So this is this whole thing where you've got to rewrite your, say, plus state as 0 plus 1, minus is the same but with a minus sign, and then you invert this, put in the formula, rearrange some coefficients, and you get that. Okay, then now we can simply read off from here that the average value of R has to be, so if we measure plus, the probability of that is A0 plus A1. That's the probability of plus, right? The value that you assign to that is R0. And the probability of getting the other one is this one squared. And the value that you're going to give there is R1. And basically that's our answer. Okay. Because that's the modulus squared of that gives the probability of getting that state. Modulus squared of that one is probability of getting that state. And our R is defined like, so if you get plus, then our value is R0. You get the minus state, then our value is R1.
Yeah, so R is R the sum of the whole probability, like that?
R is the sum.
Oh, R is the probability.
No. R is like the value that you assign to it. So R would be the thing that's like, okay, my state is, say, 0.
So R is the total value. Oh, so it's probability times each individual value of the R.
Yeah. So, for example, this, I could place my boxes at, here's my state 0, here's my state 1. I could place my boxes anywhere, right? Even like, -5 or something. It's just the value that I'm giving it, because whenever you're taking an average over something, you're averaging over values, If you're averaging over heights of people, then it's like, 170 centimeters, stuff like that. The value of the thing that you're averaging is R. Probabilities you work out by looking at the wave function, in the modulus squared. Okay, so that's method 1. Now let's do it method 2, which is just substitute into this formula. And in a way, this kind of whole notation of why we're using, this bras and kets and stuff like that, and why we are, basically why we're using this whole notation can be kind of explained, because basically it's like, what's the average of R? Well, that looks quite a lot like this formula. So that's why we use it. Okay. It's kind of like good notation, you know, suggests the next step in whatever you want to do. Like, because you can't possibly remember all these things. You need a sort of a little bit of a hint. So you go, I want the average. Oh, it kind of looks like that formula. So that's kind of why we use this. Okay, so now we can do this. Okay, so let's do it the kind of the vector notation way, if you like. So let's write our state. So let's just substitute all these things here. So a conjugate vector for the state is A0 star plus A1 star. Okay. Our R is that. Okay. And our state is A0, A1. Okay, so let's work out this part of it. Okay, so we kind of just multiply out these four terms here. So we're going to get R0 plus, so this one and this one. Okay, so A0, A0, R0. This one times this one is plus and 0. And let's go this one and this one this time. So this one is going to be A1 R0 plus and 1. We'll do this one and this one. A0 R1. And last one, A1 R1 minus and 1. Okay. Now we need to substitute a couple of these inner products. So remember, plus is 0 plus 1. So that means the when you work this out, this is 1 over root 2, because basically it's that coefficient then. This one is also 1 over root 2 because they both have a plus sign. This one is also 1 over root 2. This one is minus 1 over root 2. Okay. And we can factorize these two vectors here because they're both plus. So, going to get A0 R0 plus A1 R0, okay, over root 2 and plus. These guys we can also factorize because the vector part is minus. A0 R1, so this one has a minus sign, A1 R1 minus state. Okay, so I've got that. And now we got to multiply these guys out now. Okay. So let's do that. So again we'll get four terms. So A0 star times, I can kind of factorize this one here on the fly, over root 2. This is 0 over plus. this one and this one. A0 star, let's factorize this one, R1, 0 and minus, A1 star of A0, 1. Oh, wait a minute. Oh, yeah, that's right. 1 minus. Okay. This thing is 1 over root 2. This is 1 over root 2. This one is 1 over root 2. This one is minus 1 over root 2. Okay, let's hope this works out. Yeah, so this term and this term we can factorize again. Plus A1 star A0 plus A1 R0 over this give 2. Okay, looking good. And here we've got A0 star minus A1 star. So A0 star minus A1 star. A0 minus A1. R1 over 2. And yeah, so you can see that that's equal to that, and that's equal to that. Okay. What about algebra? Okay. Yeah, and maybe I won't fully write it out, but we could equally have done this one just using matrix. So this is sort of method 2b, if you like. So I could have written this also as something like A0 star, A1 star, and our R matrix was this one, R0 plus R1, R0 minus R1, 0 minus R1, R0 plus R1. So if I did that whole matrix multiplication, then I would also get that. As above. Yeah. Okay. Anyway, so that's the point that I was trying to make, that you could do it either way. I mean, okay, so in this case, somehow this one looks far easier than this one, but well, I think it kind of depends upon how easy sort of, basically you can choose according to convenience which is going to be easy. So for this particular example, obviously somehow this had a lot of algebra, this one didn't, so this is sort of, well, partly because we already, I just wrote this step down in because we did it before, right? In a way, had I had to derive all the kind of transformations, this would have been longer. In a way, that whole transformation is all just here in the algebra somewhere. Okay. All right. Hope that's clear. So let's see, where are we up to now? So that's basically what I want to say there. Okay, and yeah, so if we wanted to work out other quantities like variance, again, we could just do it either way. So we could, of course, change the state to the same basis as R, and then, of course, in that case, things like the square of the R matrix is, going to be quite simple, because when you square this matrix, of course, it's just R0 squared, R1 squared if you're working in the basis of the matrix. But if you work in the basis of the state, then you have to square this matrix. And it's going to be a little bit of algebra there to work out what the square of that matrix is, because it's got a few more terms. So you can either work in, you can work in either basis and you still get the same result. Okay. Alright, that's probably a good place to break, because this is kind of a different, well, yeah, this is also talking about qubit observables, but I think we're better off starting that for the next lecture, yeah. Okay, so maybe we'll leave it there. Any questions?
I think that there's a model that you said that the atom is trapped in a certain place by the laser. So how can you do that? So
Yeah.
Why there is discrete position instead of continuous?
Yeah. Well, yeah. Well, actually, always there is a continuous position. In fact, essentially, what you do is you make, by shining this laser. It's a little bit not sort of intuitive, but by shining the laser, you can actually make the positions of these, where the laser is strong, kind of a low energy point in terms of this whole space.
So it is in its most stable.
Yeah,
place.
kind of, yes, yeah. And so, yeah, it's not that the atom can't physically go anywhere else, and it's impossible for it to be somewhere between the lasers or between the boxes. It's just that those are kind of the low energy positions, and you would have to give the atom kind of more energy to be in all these other positions. And so it's just more favorable that it's in those positions. It's not that you physically make it impossible to be not in those positions.
So how do we make sure that it's in quantum state instead of the classical state, that it is something in between those boxes?
I think it's basically by kind of cooling the atoms so that it doesn't have enough energy itself to be, somewhere else. Right? So essentially, in terms of the sort of the energy landscape, essentially what you're doing is position, and if this is energy, you kind of make the energy landscape look like this. And then say now you cool the atom down so that the energy that the atom has is only sort of around about here. Right? And then if you do that, then basically you exclude the atom from being in these other places in between these lasers. And so it has to be kind of here or here or here. And then quantum mechanically, then it becomes possible that it's in some superposition of these states. And it's, as I mentioned, it's not that, well, even this box kind of example, it's not that even in regular life that's impossible for it to happen. It's just that such a state is actually very susceptible to being destroyed by noise. Okay, so even if you started in that state, it immediately kind of noise and stuff acts on it such that it sort of forces it into one box. But by making it in this kind of environment, you put this in a vacuum, so there's not even any particles around it. There's no magnetic field. You cancel everything out. So you make it in this very kind of ideal environment. Then you can start to see these quantum effects because it's kind of a very ideal sort of kind of situation that you've engineered. But basically, to answer your first question, you basically cool the atom enough so that it sort of can't be in these other places. Sorry?
Yeah.
Yep, okay. Okay, alright. Then, thanks for your attention.